we will be recording. We'll go from current slide. All right. So, all the light coming in, it's pretty bright. A little bit of light there. That helps you or not. Helps me see a little bit better over here. All right, I believe we're in section 2.2, separable variables, top of page 48. Okay. It actually is an alternate solution to the one that they did, but I think we had already done it, okay? I think I did the alternate solution, the book did the other solution, so I didn't notice that last time. I was just setting it aside. Now, beginning then a little bit further down on page 48, in section 1.1, we saw that a solution curve may be only a segment of an arc of a graph of an implicit solution g of xy is equal to 0. So basically we're going to solve an initial value problem. I don't know why they had that verbiage to start. Let's just solve an initial value problem. Let me get my pen set up. Okay. Solve this initial value problem. dy dx is equal to negative x over y. Not the same one we had before, just making sure. That isn't x there, and that's divided by. Okay. Now, our initial value, y at 4, is equal to negative 3. I don't know, there's something about that that doesn't smack of initial value. It's just some value, okay? Maybe it is the first one, but it doesn't look like it. It says y of 4 is equal to negative 3. Now, how would you get started on that one? Any suggestions or ideas? What's the title of this section? Okay, in other words, let's get all the y's on one side and all the x's on the other side. Okay, now to get x's on the other side, we write it in differential form, and at the same time we'll be multiplying by y. So I like that idea, multiply by y. Okay, and we'll write it in differential form. In other words, bring the dx to the other side, which looks like we're multiplying by dx, but we would never think of doing that, would we? Okay, we're writing it in differential form. This gives you y dy is equal to minus x, and we're writing that in differential form, dx. Okay, and then we can integrate both sides of the equation. Okay, what does the left-hand side give you? In fact, I'm going to do something just a little bit differently from what I just did. I'm going to go put the minus sign outside. Okay. So what's the antiderivative of y dy? Y squared over 2 is equal to negative x squared over 2 plus some constant c. Remember, you always have to have a plus c for indefinite intervals, okay? But you only need one. You don't need one for the y and one for the x, just one, usually with the x's. Doesn't matter, but that's usually where we put it. But we do have a specific point that's on the curve, 4, negative 3. So if we plug those values in, we should get the value for c. So what does this come up with? By the way, y is a function of x, so this is your x, and this is your y. Plug them in, plug them in. Second, 9 over 2 is equal to negative 16 over 2. Now, that minus is before you do the x squared. Do the x squared first, then do the negate. Okay? All right, plus c. Okay? What would you do to solve that? Okay. All right. Now, to answer what De Silva said, I would move the 16 over 2 to the other side, isolating the c, or multiplying by 2, either one. Which way you want to go? Multiply by 2. So this will be 9, and that'll be a 2c. So we got 2c is equal to, now I'm moving it to the other side, 9 plus 16. I skipped a few steps there, but you see what I did? Okay, so c then would be equal to 25 halves. Okay, so you go back to your original equation, y squared over 2 minus is equal to minus x squared over 2 plus 25 over 2. You know what? I think I don't like all those 2's in there. Why don't we just do it as x squared plus y squared is equal to 25. How about that? What does that describe? Say again? Okay. Now, technically, half a circle. Because a circle would not be a function. Okay. So, we do know that when x is 4, y is negative 3, so it's going to be at the bottom half of the circle. Right? Because you got a negative 3 for y. So it's the bottom half of the circle of radius 5. Okay? Can't be the whole circle, not a function. And we are assuming that y is a function of x. But because our initial condition, whatever that point is, when x is equal to 4, y is equal to negative 3, you're down here. The only way you will get a function value is to be like that. So let's see what they found out. Yeah. Y is equal to negative square root of 25 minus x squared, and that goes from minus 5 less than or equal to x less than. Now, I'm not certain why they have just strictly less than signs there. So they rewrote this as y is equal to minus the square root of 25 minus x squared, and then they put the domain minus 5. They put less than x less than 5, which is what I described, except I don't see why they can't include the equal sign. I do so see that. Our original problem had x over y, so y can't be 0. And if x were equal to plus 5 and minus 5, it would be equal to 0. But in our original problem, it cannot. That's why they did that, okay? Sorry about that. Mathematically, up to that point, wouldn't have been an issue, except your original problem had minus x over y, and y could not be 0 in that case. So, yeah, they're right to leave off the equal sign. Does that make sense? This part right here would indicate to you it's half a circle. And that part indicates it's got to be the bottom half. And that part indicates you can't include x equals plus or minus 5. And we got Nigel here. All right. increase the class size by 50%. Way to go. We just finished example 2, top of page 48. Okay? Now, there is something said next about losing a solution. Some care should be exercised in separating variables, since the variable divisors could be 0 at a point. Specifically, if r is a 0 of the function h of y, then substituting y is equal to r into dy dx equal g of x h of y makes both sides equal to 0. In other words, y equal r is a constant solution of the differential equation. But after variables are separated, the left-hand side of dy over h of y equal gx dx is undefined at r. As a consequence, y is equal to r might not show up in the family of solutions that is obtained after integration and simplification. Recall that such a solution is called a singular solution. Okay? Almost sounds like a lot of blah, 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 doesn't it? But there is some value in that. Sort of the same thing we just did. We noted that you could not have y equals 0, and y would be 0 if x were equal to plus or minus 5. It's sort of like that. You have to just watch for things and make sure you don't introduce something that's can't happen. Okay? So let's clear all this ink from the slide and move on to example 3. We have dy dx is equal to y squared minus 4. All right. Now, what might you do in one like that? Any ideas, suggestions, things you want to try? Where would you go from there? Anywhere? You just hang where you are. Give me just a wild guess. What might you do? Say again? Okay, actually this already indicates that's a derivative. So I wouldn't take another one. That just gets more and more confusing, I think.
Split up dy dx.
Split up dy dx. In differential form. I think it's a good idea. Let's try that. Dy is equal to y squared minus 4 dx. Now, just to make that look a little better, I'm going to write it like that. Now what? Exactly, because you're trying to separate the variables. Now, remember, you can only separate products, okay? And this is a sum or a difference here, except you can keep that together as one factor, because indeed we can factor. So let's divide both sides by y squared minus 4. And here we get rid of the y's on this side and put all our y's over there. Now, what would we do next? Once you got everything on one side, you integrate, right? I can do the right-hand side. The left-hand side, left-hand side is going to take a little more effort. What might you have to do with that? Well, it's one thing that pops out at you, I hope. Y squared minus 4. Ah, yes, that can be factored as y plus 2 times y minus 2. Does that lead you to think anything else? How would we solve a problem like that? Do the initials PF mean anything to you? I just made them up. Well, my dad's initial, Pat Fowler, but yeah. How do we do integrations like that? Not by parts, very similar to sounding to that. Partial fractions, exactly. So let's take this one up here and do a partial fraction. We got dy over y plus 2 times y minus 2, right? Now, we want that to equal to, or do y'all want to leave off the dy? Let's leave off the dy. Let's just maybe let's make it 1 over that. You okay with that? That's the integrand, the dy is part of it's going to follow it. Now, we're hoping that's going to be, say, a over y plus 2 plus b over y minus 2. You okay with that? We're hoping that complicated fraction will split into two simpler fractions, right? Where do we go from here? Yeah, let's multiply both sides by y plus 2 times y minus 2. Multiply this by y plus 2 times y minus 2. I wish I'd left more room. Multiply this by y plus 2 times y minus 2. Okay? Now, here, everything goes out except 1. That's sort of nice, isn't it? Over here, the y plus 2's go out, and you're left with a times y minus 2, right? And here, the y minus 2's go out, and you're left with a plus b times y plus 2. Buy it? Okay. Now, that's a lot simpler looking form than what we had to begin with. Now, what do we do with that? It almost seems illegal to me, but it's legal in most states anyway. What do we do? What if we let y equal 2 in that equation? Here, it's still just 1, because 1 doesn't change when y is equal to 2. What happens with that one, though? That is a y there that's... Ooh. What's that? Yes, that one becomes 0, and then you've got 4b. Or not 4b. No, that's something else, okay? And guess what b would be then? b is equal to 1 over 4. Okay? And what's another thing we could do? Go back to this equation. But this time, let's put y equal negative 2. The 1 stays a 1. What happens here? Negative 4a, right? Plus 0. So this implies that a is equal to negative 1/4. Okay. So let's go back up here, and this says that this would be, I'll write it down here, a the integral of a was negative 1/4 minus 1 over 4 times y minus plus 2 plus 1 over 4 times y minus 2 dy. Now, I was starting before I wrote any of that is to pull the 1/4 out front, and I think I will. No reason messing around with extra fractions we don't have to. And I'm going to rearrange the order. Is that okay? I'll make it 1/4 the integral of 1 over y minus 2 minus 1 over y plus 2 dy. Okay, now, I think I'd just as soon write that as two different integrals, wouldn't you? Like the dy here and a dy there. Drop that one and drop this one. I think we can do that, can't we? I think what I will do, though, is put a big bracket around these two. Okay? Goodness gracious. What does this turn out being? 1/4 antiderivative of 1 over y minus 2. Absolutely, natural log of y minus 2 minus natural log of y plus 2. Okay? Now, there's a couple of things you could do here. I don't know if you want to do them, but you could do them. One of the rules of logarithms is that you could write that as 1/4. The log of a the difference of two logs is the log of a quotient. You remember that one? Log of a quotient is the difference in the logs. So this would be the log. And by the way, when we do logs, we really need to put absolute value signs around those logs because they don't make sense. You can't take the log of a negative number. Okay? So this will be the natural log of y minus 2 over y plus 2. Okay? Now you could take it one more step and call that all raised to the 1/4 power. Okay? But I don't know which is better. What we've got to do, by the way, is do the other side as well. And I just need more room. So I think I'm going to erase some. I think I'll erase that top line. I don't think I need that anymore. I'm going to keep my original and erase. Goodness gracious, this is not erasing. Okay. All right. The left-hand side became 1/4 natural log absolute value y minus 2 over y plus 2. Okay? The right-hand side, that was just simply this integral right here. Integral of dx, what's that? X. Okay? Is equal to x. And then usually here we put a plus c. Now, I'm trying to think if we'd be better off with the plus c over there with a more complicated function, which would be perfectly fine. But I think not. I mean, what's the difference? There's no way you can set this up as an explicit function, I don't think, of y as a function of x. I think you're left with something like this. But, notice I said losing a solution. Obviously, in this form, y can't equal -2, nor can it equal +2, because you can't take the log of 0. Ever. Even with absolute value bars around. So basically it says y can't be plus or minus 2, which we see right here. They can't be plus or minus 2 here either. Okay? Now, up here though, there's no problem with this. dy dx equals 0, that would be a constant function. So in doing our separation of variables, it sort of looked like we lost two solutions. Y is equal to, in fact, when we divided both sides by this, we lose two solutions. Y is equal to +2 and y is equal to -2. In this original form, there's no problem with y equal plus or minus 2. Then you would have just a constant function, because the derivative of a constant function is 0. Okay? But for the rest of the solutions, you would lose it. So I think that may also be what they call singular solutions or something like that. Now, they did a lot of other stuff, okay? And let me just suggest to you what that was. They took this and multiplied 4 times both sides of this equation, okay? But then 4c is the same as c, so, I mean, it's just a constant. 4c is just a different constant. So rather than do that, we would have the log absolute value y minus 2 over y plus 2 is equal to 4x plus some other constant, but let's just still call it c. It's just 4c from before. You could have named it c1. That's what they do in the book, but that gets a little confusing. But at that, if you don't like having a log function there, we can take the log of both sides. So I'm going to erase me some more room. I'll erase pretty much all this. Okay. You can take that, you can exponentiate both sides, okay? And if you do that, you get y minus 2 over y plus 2, and I guess technically you have to keep the absolute value bars on there, but they don't, okay? Is equal to e to the 4x plus c. Okay? Because raise e to both sides to lose the logarithm. Because e's are a little easier to mess with than logarithms. Now, if you lose the absolute value bars, okay, then the right-hand side is either the plus or the minus of that. And that's what they do to, in the next step, y minus 2 over y plus 2 is equal to plus or minus e to the 4x plus c. Okay? A one-parameter solution, and obviously, again, y can't be negative 2. We already knew that. Okay up there, but not anywhere else. Okay? Neither can y be 0, because e to the anything is never 0. E function stays above, e to the minus stays below. Can't ever be 0. So, I'm sorry, it's either like this or like this, okay? But never is equal to 0. So y can't equal 2 again, okay? Now, okay. They do take it one more step. And you can write this in terms of this seems like more trouble than it's worth, but let's do it. Okay. Okay. I don't think I need this either, so let's clear this out of the way. Basically, we're just working with, or as I can remember one professor saying, manipulating it around some to get it to do either what we want or to have a form that we want. Okay? And here's what they do here. Y, let's multiply both sides of this equation by y plus 2. Okay? Okay. Yeah. Sometimes the eraser picks up and sometimes it doesn't. Okay. Multiply both sides of the equation by y plus 2. And that gives us a y minus 2 is equal to I think I'm going to write it this way. Y times plus or minus e to the 4x plus c plus 2 times e plus or minus e to the 4x plus c. Okay? Now, what I'm going to do next is add 2 to both sides and subtract this y term from both sides. So add 2 and subtract y okay. My thing won't come up. There we go. Well, this thing is pretty frustrating. Okay, there's a mark there that won't disappear. I don't know why. Okay. I'll try something else. I'll try to erase all that. Well, just the mark stays. Okay. So I added 2 to both sides. And that leaves, and what I want to do is subtract y plus or minus e to the 4x plus c minus y plus or minus e to the 4x plus c. Sure looks like a 2. I don't know how that became a 2. Four x plus c. Okay. Now, this is just so messy. What we have here, these 2's go out and these y things go out. Okay? So what we have now is y minus y times plus or minus e to the 4x plus c is equal to 2 times one plus or minus e to the 4x plus c. Okay? I should have actually factored this one too. In fact, I'll do it. Factoring out the y. What we have is y times 1 plus. Okay? And then what we're going to do is divide both sides by this. 1 plus e to the to the 4x plus c. And that's what we've got here. 1 plus or minus e to the 4x plus c. Okay. Now, I don't think you need the plus or minuses in there. You just need to determine one or the other. One of these becomes a plus and one becomes a minus. And I'm trying to think if there's any reason having one rather than the other, top or bottom. I'm sure there is. I just can't think of it now. These have gone out here. So y is equal to 2 times get it to clean up a little bit. Too much. Okay. And that's the answer they got in the book. Okay. Oh.
They just,
Yeah. The e to the c. Okay. Another little trick here, and really we should have done it anywhere up above here. This thing right here, e to the 4x times e to the c. E to the c is just a constant, so just move that here and wipe it out there. So that's a c here, a c there, and lose the c's in the other places. With exponents and in a certain sense with logs, you do lose those. Okay. It says here, however, y is equal to negative 2 is a singular solution. It cannot be obtained from this because that just won't work. Ooh, didn't mean to have the erasure on there. Okay. Lost the equal sign. Okay. And the solution y is equal to 2 is a member of the family solutions when c is equal to 0, because then you have 2. So that one you don't have to do anything special to. But y is equal to minus 2, you have to go back and put that in. The latter solution was lost early because solution process, inspection 5, clearly indicates that we must preclude y is equal to plus minus 2 in these steps. Okay. We'd already talked about that, but this is in the simpler solution. Okay. Now, I'm sure there's some sort of way to analyze this and decide where your plus and the minus is going to go. But for the moment, I can't see what it would be and what would be the advantage of going over it in gory detail. Those are your solutions, so we'll just leave it there. All right, let's go to something else. It, on the one hand, looks a little more complicated, but the other hand, it may be a little more straightforward. Let's solve this one. E to the 2y minus y, well, times the cosine of x dy dx is equal to e to the y sine of 2x. Okay. Now, this truly looks like an initial condition. Y of 0 is equal to 0. Okay, y on the first instance of anything is equal to 0. So this is, they call it an initial value problem. This truly is not a boundary or something else, an initial value. Okay, what in the world can we do here? What would be your suggestions? Any whatsoever?
separate your variables.
What's that?
Separate your variables.
Separate the variables, absolutely. And how would that come about? Okay, let's divide cosine x here. And of course, that's going to also move it over here. So we lose this on this side, and we do have only y's here. But we still got a y over there. divided by e to the y here and here. Okay, and now the e to the y's go out here. And then write in differential form is what we say, don't we? E to the 2y, and let me make sure I wrote that in the right place. Minus y, yeah. Minus y over e to the minus y dy okay. Did I copy it wrong? No. The original problem, e to the 2y minus y, and that just brings down here. Oh, that, I'm sorry. I don't know. I don't know where that came from. I think I was just used to saying minus y, e to the y, divided by e to the y. Okay? And over here, we'll have sine 2x over cosine x dx. Now, does anything bother you especially about that? I get the feeling we can live with this, maybe okay. Little bit of problem there. The signs of double angle formula and single angle formula don't always click too well together. So I would be real tempted to write that sine of 2x as 2 sine x cosine x. Remember that? And I don't know in this book if they have any of those things. I don't really see any trig identities in here. Laplace transforms. Don't see any. I think you have to pull up your old calculus books for that. But if I'm not mistaken, remember what this is? 2 sine x cosine x. You remember that? If not, see if you can remember this. What is sine of x plus y? Sine x cosine y plus cosine x sine y. Ring a bell? Oh, come on now. Matt, rescue me. You were in my trig class. Please say you remember that. Yeah, he'll say it, but he don't. Okay. Don't remember that as your trig identity. See, with cosine, it would be cosine of x plus y would be cosine x cosine y minus sine x sine y. Okay, this is plus there. If you did that, and then the next phase is then say, well, then let y equal x. So then this would be sine of, if y is equal to x, it would be x plus x, it would be 2x. And this would be sine x cosine x plus cosine x sine x, that's 2 sine x cosine x. Okay? So basically, that I'm pretty sure is what it is. Now your cosines go away. And that's a lot nicer. Okay? A whole lot nicer. Now, is there anything that can be done on the left-hand side to simplify a little bit? Okay. I would split this as being e to the e to the 2y over e to the y minus y over e to the y. Right? That's legal, right? And this then would just be e to the y, right? And this would be y e to the minus y. Okay? So I think that's what I would do next, is say this is e to the y minus y e to the minus y dy is equal to 2 sine x dx. All right. I don't know if that's a lot better, but it just looks a little better to me. Okay? Now what we do is try to integrate both sides. Okay, I pulled the 2 on the outside there. Now, the first one on the y's on the left, I can do pretty nicely, I think. What's that? Integral of e to the y dy. E to the y. Okay, that's nice. Okay, so this is e to the y. But that second one, oh man, what are we going to have to do with that? Second? In some senses, this isn't a derivative, so you can't do it directly, but any ideas? Let me rewrite it slightly. Minus the integral of y e to the minus y dy. Let's go and do the right hand since we're here. What's that going to be? Minus 2 cosine x. And probably we'll put a plus c in that. We may decide to move that c around some like we always do. But we got to figure out what to do with this. Does anyone come up with an idea? Some of you were mentioning it early when it wouldn't work for that last one we did. It sounded like what we did for the last one.
Oh, yeah. You said that I need some more
Integration.
Yeah.
Integration by parts. All right, remember? Now, substitution I don't think will do it. Integration by parts will. Now, remember, integration by parts is almost like making, kind of like making two substitutions, not quite. What do we do? And it comes from the product rule. That's how you get it, but it's going backwards is integration by parts. And how did you do that? We started with let x equal something and let but not x. How about y? Let's see. No, I think it's used, didn't it? Didn't we use u? Yeah, I believe it's u. So I was starting to use x, and then I said, nah, let's not do that. It'd be too confusing. Because you have x's on the, let u equal something and dv equal something else. Which you reckon, and I can tell you the dy is going to go with the dv, right? Got to. Okay. Now, remember what the rule was. What we're going to do next is figure out what du is by taking the derivative. And we got to figure out what v is by integrating. Now, taking derivative a lot of times gets simpler, not always. Doing the integral sometimes gets more complicated. So what we want to do is pick our variables, our parts here, integrating by parts. Pick our parts so the part over here gets simpler, the part over here doesn't get much worse. What will simplify when you take a derivative? Y will, exactly. Let the u be the y part, and then dv would be the e to the minus y dy. That's the rest of it. Then, what is your du? Help me, help me. If u is y, what's du? dy, right? And, now we do the other side, v is equal to what? Take an antiderivative of e to the minus y, and what do you get? Say again? It's a minus e to the minus y. Do you buy that? If you don't, take a derivative of this and see if you get that. Derivative of this would be minus e to the minus y, chain rule times a minus 1, e to the minus y dy. Yeah, that works. Okay. Where do we go from there? Integration by parts. Remember, this did initially come from the product rule. So we wound up with the product of the u's and v's, not in an integral, minus the new v du down here. Dr. Bryant was doing it in the Cal 2 class Monday night, I think it was. Okay? So what we have here, this one becomes uv, which is minus y e to the minus y, minus the integral of v du, which we have a minus and a minus, so that makes a plus e to the minus y dy. Okay? When you do the bottom row here, normally it's a minus there, but then the v part is a minus 2, so that makes it a plus the integral of e to the minus y dy. That one I can integrate. What does that integrate to? Antiderivative of e to the minus y. It becomes minus e to the minus y. That's what's so pretty about exponentials. They just give you the same thing. If there's a chain rule thing, you have to do that too. Okay, so let's go back. I think I'll do it up here. See what we wound up with here. Here we had e to the y. Then we had a minus. This minus negates that minus, and that makes a plus y e to the minus y. But this minus also makes that a minus, no, but that became plus again e to the minus y. That's everything on the left now. On the right, we've got is equal to minus 2 cosine x plus c. Now, at least on the surface, this doesn't look like one that's going to come out nicely as y as a function of x. I just don't think it's going to happen. Let's take a look at the book and see if they managed to get that to happen. Oh, we haven't done our initial condition yet. So I think we've got that, yeah, we've got that done so far. Okay? Now let's plug in our initial condition. Y of 0 is equal to 0. So this is going to be e to the 0 plus 0 e to the 0, which is going to be 0, plus e to the 0 again is equal to 2 times minus 2. What's cosine of 0? 1. So that's minus 2 plus c. What's e to the 0? 1. This is 0. What's e to the 0? 1. So you have 2 equal minus 2 plus C. C is equal to say again? Add 2 to both sides? Two is equal to minus 2 plus C. Add 2 to both sides. C is equal to 4. Okay, high level math today. 2 plus 2 is 4, huh? No, I don't. Yeah, this is 1 plus 1 is 2. Okay. So, man, let's erase some stuff here so I can write my final answer in here. I'm going to erase it right up here. I think that will give me plenty of room to do so. Okay. We got our C now is 4. So what we have as our final answer is e to the y plus y e to the minus y plus e to the minus y is equal to minus 2 cosine x plus 4. Or they write it as 4 minus 2 cosine x. Yeah, that's fine too. And I think that's exactly what they got. Yes. Now, they have a little blurb here on use of computers, and they're referring back to remarks at the end of section 1.1. So I'll let you go and tie those together. It's talking about a computer algebra system, CAS. I personally don't have a copy. I don't know if you do. If you do, use it, enjoy it. But we don't. I don't. So when the pictures in the book show the family of curves for certain values of your C. I don't know which those are. The one that crosses the origin is when C is equal to 4, and the one right below that, no, 2 below it, is C is equal to 2. So the one in between must be C is equal to 3, and then as you're going up, C is equal to higher numbers. As you're going down, C is equal to lower numbers. It looks like anyway. So we were really only interested in the C equal 4, because that's the one we landed on. And there it is. Because y of 0 is 0. Goes through the origin. Okay. If an initial condition leads to a particular solution by yielding a specific value of parameter C in a family of solutions for first-order differential equations, there is a natural inclination for most students and instructors to relax and be content. Would we ever do that? Okay. However, a solution of an initial value problem might not be unique, as we saw in example 4 of 1-2. I don't remember that, but you can go back and check. Okay. That the initial value problem, and this is back when they were just showing us answers. Now let's actually do the answers. We'll clear all this out of the way. Here was the problem then. dy dx is equal to xy to the 1/2 with the initial condition y of 0 equals 0. Now, doing what we do now, what would you do to this problem? Well, the last time they gave you answers. This time, let's find their answers. What would you do? Separate. And how would that come out? How would that come out? Okay, that was my first inclination too, and that's exactly what I'm going to do, but I don't like having a radical in the denominator, and that's what the 1/2 stands for, right? So I'm going to write that as y to the minus 1/2 dy. Are you okay with that? That's going to be easier to integrate than having the dy over y to the 1/2, okay? I think. Equal to what next? X dx. Okay, and then what? Integrate both sides, right? What does the okay? Oh my God, it's so blank. What time do we finish it? 3:15. So we're almost there. Let's get this one done. What would this give us?
2y to the 1/2.
Okay. I believe it's got to have a minus in there too, doesn't it? Minus 2y. No. Okay. Integrating, yeah. No, you're right. It's just a plus 2. Okay, sorry about that. Okay. Yeah, 2y to the 1/2. Because when you take the derivative of it, 1/2 times 2, it's 1, y to the minus 1/2. Yeah, you got it. Is equal to? Equal to? You did the hard one. X squared plus c, right? Over 2. X squared over 2 plus c. Right? Now let's plug in y of 0 is equal to 0. So this would be 0 equals 0 plus c. Looks like c has to be 0, doesn't it? Sure looks that way. Okay? So let's rewrite a little bit here. And that would be 2y to the 1/2 is equal to x squared over 2. All right, now if we multiply both sides by 2, no, divide both sides by 2, you get y to the 1/2 is equal to x squared over 4. If you squared both sides, that would give you y is equal to x to the 4th over 16. Right? And with, that is a solution. That's one of the ones they came up with. But remember also, what satisfies this as well is y is equal to 0. X equals 0, y is equal to 0, y is equal to 0. That's certainly also going to be a solution. Because 0 to the 1/2 is 0, and this would be 0. 0 is equal to 0. Yeah, that works too. So we do have two solutions, even though we only had a one-parameter system. Okay? And again, one of these is called a specific, I believe it is. The trivial solution, y is equal to 0, was lost when you divided by y y to the 1/2. When you did that, dividing by 1 to the y to the 1/2, you couldn't do that if y is equal to 0. But it obviously is a solution, because if x is equal to 0, y is equal to 0, the derivative is 0. So indeed, we did lose one when we did that. So what you have to do is You just have to include them both. Okay. I think what we're going to have to do is stop there because we're out of time. Pick up at solutions defined by integrals. Okay. And there's example 5 showing up there. Homework exercises in 2.2. Do any of the odds 1 through 21, any of the odds 23 through 27, do 29. Whoops. Actually, they're saying do as example 5. We haven't done example 5 yet. So hold off there at 27 will be your last. Now, before you go, I believe last time we had the issue of, I didn't have time to get your chapter 1 test done. But since then, I have had time to complete it, and I sure hope it's in my stack here. It's supposed to be. There it is. Y'all can breathe easy again. Now, I'm going to say a little bit more. It's all on one page, but you're going to need a lot more room than this. Okay? So, if you can write on the back, you can attach additional pages. You're going to have to do. The first one is just take the derivative of that function. Right? Just really easy. Don't try to make it any harder. Okay? That's my job. Okay. The second one, you take the first derivative and second derivative, and then what you have to do is figure out a way to write the function with no c's in it. Okay? We did something like that in the text, and it's in the homework and stuff. So work on that. If you have trouble with them, find one like it in the book, and I'll try to work through that in the book. Okay? But that one's, I guarantee you're going to need more room than you've got there. That's what the third line said. F of x, f of y, y prime, y double prime. It's just a form. That's going to be equal to 0, and it's going to have only y's, y prime, and y double primes in them with no c's. Okay? That's what it means. And then combine these derivatives with y as a linear second-order differential equation that is free of the symbols C1 and C2. So you don't have the C's on it. Number 3, determine by inspection at least one solution of the given differential equation. You could probably come up with 2 pretty easily, but do at least one. Okay? Number 4, verify that one parameter family is an implicit solution of the differential equation. So basically, you do an implicit differentiation of that first equation there and see if you can get it to look like the second. Okay? Again, I haven't given you enough room to do all that on this page, so you're going to have to attach a page, I think. Okay? What is the slope of the tangent line? I think that's, again, you'll probably need more room, but you can do it, I believe. Problem 6 and 7, you're to do the same thing with both of those. And then number 8 and number 9, just do it. What is requested there? And again, you have at least a week to do this. So look this over. If you have any questions on Wednesday, bring them in Wednesday. I'll try to clear up any of those questions. And then, now, will any of you see, who are we missing today? Antonisha and Charles, no one's seen yet, I don't think, except me. And Jonathan. I'm not going to see Jonathan. Okay. When and if you see them, tell them there's a test to be picked up. I'm going to try to send the others to the other 2. I'm not even sure they're still in the class, but I'll try to find out. Okay, good deal. Any questions? All right, we will see you Wednesday. I've got to get out of Dodge so Dr. Bryant can have his physics class. So let me end this.